I am M. Satya to the lecture on aberrations in optics. I am M. Satyavani, lecturer, Department of Physics, DNR College, Bhimavaram. Aberrations are nothing but they are the defects in images formed by a lens or number of system of lenses. Aberrations means deviations from the actual size, shape, position or color of the image produced by a lens in comparison to the object. They are divided into two types. Number one, monochromatic aberration, and the second one is chromatic aberration and monochromatic aberrations. Chromatic aberration is due to the dispersion of white light. If monochromatic light is used, this defect is eliminated. But there are some other defects in images even if monochromatic light is used. These defects are known as monochromatic aberrations. Monochromatic means monochromatic light means a light having single wavelength and a single colored light. Even if you use single colored light, then some other defects may arise. They are known as monochromatic aberrations. There are 5 types. Number 1, spherical aberration, astigmatism, curvature and distortion. First of all, I discuss about chromatic aberration. Chromatic means color. This defect arises due to color. We know that white light is a composite light. When it is incident on a convex lens, it splits up into 7 colors. This phenomenon is known as dispersion. We know that the focal length of a lens f is given by 1 by f is equal to mu minus 1 into 1 by r1 minus 1 by r2, where f is the focal length, mu is the refractive index of the material of the lens, r1 and r2 are radii of curvatures. If you observe this equation, focal length is inversely proportional to refractive index. The refractive index, we know that the refractive index mu changes from color to color. Refractive index for violet is greater than refractive index for red, that is mu v is greater than mu r. Therefore, focal length which is inversely proportional to refractive index, then fr is greater than fv. That means different colored images are brought to focus at different positions on the principal axis as shown in the figure. In this figure, if you observe the figure, you can see that the violet image is formed at this point and the red image is formed at this fr. The remaining colors in the images in the VIBGYOR are formed in between violet and red. That is, different colored images are brought to focus at different positions on the axis. Thus, the image formed by the lens for a parallel beam of white light appears to be blurred. That is due to overlapping of number of colored images. This defect in lenses is known as longitudinal chromatic aberration. That longitudinal chromatic aberration is nothing but variation of focal length with respect to color. The difference fr minus fv is the measure of longitudinal chromatic aberration. In the above figure, the rays are parallel rays. That is, if the object is infinity, the rays are parallel. But if an object is situated on the principal axis, then the white light coming from the object, when it is incident on the lens, it undergoes dispersion. Then different colored images are formed on the principal axis as shown in the figure. In this case, violet image is here and red image is here. Then longitudinal chromatic aberration is equal to IV minus IR. This is about longitudinal chromatic aberration. The next one is lateral chromatic aberration. As this is the object AB, the light from the object is allowed to incident on the convex lens, then it undergoes dispersion, different colored images are produced. the distance of the violet image is from the lens is this much, and the distance of red image is greater than the distance of the violet image from the lens. That means object distance is same for all colors, but image distance is different for different colors. We know that magnification is nothing but it is the ratio of size of the image by size of the object, or distance of the image by distance of the object. As different colored images have different image distances, then their sizes are also different. If you observe this figure, this red colored image is longer than the violet color image. This defect in images is known as lateral chromatic aberration. This difference in length between ABVV and ARBR is a lateral chromatic measure of lateral chromatic aberration. In this way, these two defects, that is longitudinal chromatic aberration and lateral chromatic aberration, are combinedly known as chromatic aberration. That means chromatic aberration is nothing but it is the defect in images when white light is used, that is due to variation of refractive index with respect to color. Color means different wavelength, difference in wavelengths. This is about chromatic aberration. Next, expression for longitudinal chromatic aberration. Then what is the amount of longitudinal chromatic aberration? We have to derive the expression for longitudinal chromatic aberration. Consider a lens of focal length, mean focal length f, and FR and FV are the focal lengths for violet and red. Mu V and mu R and mu are the respective refractive indices. Then according to Lensmaker's formula, for red rays, this is the equation for red rays, 1 by FR is equal to mu R minus 1 into 1 by R1 minus 1 by R2. This is the equation for violet rays. This is the equation for mean ray. For red and violet, the mean ray is yellow. These are the three equations for red, violet and yellow rays. Then we have to calculate FR minus FV. For this purpose, subtract equation 2 from 1, we get 1 by FR minus 1 by FV minus 1 by FR is equal to mu V minus mu R into 1 by R1 minus 1 by R2. Next, by solving these equations, we get FR minus FV by FR FV is equal to mu V minus mu R by mu minus 1 into 1 by R1 minus 1 by R2. Then in this equation, there is mu V minus mu R. By multiplying and dividing this equation by mu minus 1, we get this factor, mu minus 1 into 1 by R1 minus 1 by R2. This is nothing but 1 by F according to Lensmaker's formula. In VIBGYOR, if we observe the focal lengths for different colors, they are in GB. They are in GP, geometric progression. That means if ABC are in GP, B square is equal to AC. Similarly, if you find out the values of FR, FV and mean color F, then they are in GP. Therefore, F square is equal to FR, FV. If you substitute the value of F square in place of FR, FV, we get this equation. Then by simplifying this equation, we get FR minus FV is equal to omega F. We know that FR minus FV is known as longitudinal chromatic aberration. From this expression, we can say that the longitudinal aberration, chromatic aberration FR minus FV is the product of dispersive power and the mean focal length, or the focal length of the mean ray. This is the expression for longitudinal chromatic aberration in case of a thin lens when the object is situated at infinity. Next, the next concept is elimination of chromatic aberration. We have to find how this defect is eliminated. Elimination or minimization of chromatic aberration. Elimination or removal of chromatic aberration is known as achromatism. When two or more lenses are combined together in such a way, the combination is free from chromatic aberration, then the combination is known as achromatic combination. For the elimination of chromatic aberration, 2 or more lenses are used. That is known as achromatic combination. Achromatic combination can be made by using 2 lenses in contact or separated by some distance. Therefore, chromatic aberration can be eliminated by the following methods. Number 1, by an achromatic doublet. That means in achromatic doublet, the 2 lenses are placed in contact. The second one is by using the lenses of same material separated by some distance. These are the 2 methods for the elimination of chromatic aberration. The first case, first of all we discuss about the first case, achromatism for 2 lenses in contact using an achromatic doublet. That means elimination or removal of chromatic aberration using an achromatic doublet. First of all we discuss about an achromatic doublet. Achromatic doublet is nothing but it is a combination of 2 lenses in contact each other which produces no chromatic aberration. That means we can eliminate chromatic aberration using an achromatic doublet. Next, this is an achromatic doublet. There are 2 lenses. It consists of 2 lenses. This is convex lens and the second one is concave lens. This is the combination of convex and concave lenses. This is an achromatic doublet. In general, in an achromatic doublet, convex lens is made up of crown glass. This is of small focal length and the second one is made up of flint glass. This is a concave lens of large focal length. Next, an achromatic doublet. In an achromatic doublet, chromatic aberration is eliminated. That means achromatic doublet shows no colors. That is, all colors come to focus at one point. Then there is no chromatic aberration. That means achromatic doublet is independent of refractive index. Next, we have to derive the condition for achromatism. For this purpose, consider 2 lenses of focal lengths f1 and f2 and dispersive force omega 1 and omega 2. If f is the combined focal length of the doublet, then we know that when the 2 lenses are in contact, 1 by f is equal to 1 by f1 plus 1 by f2. Differentiating this equation, we get this equation. This is just like d by dx of 1 by x, or then we know that derivative of 1 by x is minus 1 by x square into dx. Then similarly we get derivative of 1 by f is equal to minus 1 by f square df, and this is same as this quantity. Then if you simplify this equation, you get this equation. Minus 1 by f1 square is written as 1 by f1 into 1 by f1. Then minus df1 by f1 is nothing but, we know that dispersive power is nothing but minus df by f. Minus df1 by f1 indicates dispersive power of first lens, and minus df2 by f2 indicates dispersive power of second lens, that is represented by omega 2. Then substituting these values, we get w omega 1 by f1 plus omega 2 by f2 is equal to 0, or if you or omega 1 by omega 2 is equal to minus f1 by f2. This is the condition for achromatism in case of an achromatic doublet. If you observe this equation, the ratio of dispersive powers of the materials of the lenses is equal to the ratio of focal lengths of the 2 lenses. And the second point is, if you observe this equation on the right hand side, there is a negative sign. That means one of the as dispersive powers are positive quantities, either f1 must be negative or f2 must be negative. That means one of the lenses must be negative focal, minus indicates concave, positive sign indicates, positive sign of focal length indicates convex lens. Therefore, the minus sign indicates in the above equation one of the lenses must be concave and the second one must be convex. From this equation, we can say that the condition for achromatism in case of achromatic doublet is the ratio of the dispersive powers of the lenses must be equal to the ratio of the focal lengths. The next one is the material of the 2 lenses must be different because they are omega 1 by omega 2 is equal to minus f1 by f2. This is the condition for achromatism in case of an achromatic doublet, that is the ratio of dispersive powers is equal to the ratio of focal lengths of the two lenses. Next one, the second case for the elimination of chromatic aberration, that is achromatism for two lenses separated by a distance. In this case, we take two lenses of focal lengths f1 and f2, they are separated by some distance x, coaxial lenses. The material, in this case the materials of the two lenses are the same, therefore the dispersive for the two lenses are also the same. If take then you can take omega 1 is equal to omega 2 is equal to omega in the above expression. When these two lenses are separated by some distance x, this combination acts as a single lens of combined focal length capital F. Then we know that 1 by f is equal to 1 by f1 plus 1 by f2 minus x by f1 f2. Next, differentiating this equation, we get these equations, substituting the values of omega 1 and omega 2. Then in the above slide, in case of achromatism, df is equal to 0, as f is constant for all colors, df is equal to 0, therefore right hand side is equal to 0 and the equation becomes omega 1 by f1 plus omega 2 by f2 minus x by f1 f2 into omega 1 plus f2. Substituting omega 1 is equal to omega 2 is equal to omega and simplifying this equation, we get x is equal to f1 plus f2 by 2. Thus, the condition for achromatism when two lenses are separated by distance x is equal to f1 plus f2 by 2. That means for no chromatic aberration, the distance between the two lenses must be equal to the mean of the focal lengths or the average of the focal lengths. These are the two conditions for no chromatic aberration. First one, in case of an achromatic doublet, omega 1 by omega 2 is equal to minus f1 by f2, and the second case, when the lenses are separated by some distance, the distance between the two lenses must be equal to the average of the focal lengths. That is about chromatic aberration and elimination. First, we conclude that chromatic aberration is mainly due to dispersion of white light. Then for a white object, the image formed by a lens is colored and blurred. That defect is known as chromatic aberration. For elimination, we can use two methods. One is achromatic doublet and second one is two lenses separated by distance. In the first case, the condition for achromatism is omega 1 by omega 2 is equal to minus f1 by f2, and the second case, the condition is for achromatism is the distance between the two lenses x is equal to average of the focal lengths of the two lenses. That is about chromatic aberration.